Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about when and why do I need an operating pressure, an operating density, and an operating temperature when I carry out my CFD simulations. So, just to give you a very simple overview of what I'm going to talk about today, I'm going to start with when and why do I need an operating pressure, then move on to when and why do I need an operating density, and when and why do I need an operating temperature. I'm going to split them up like that, very straightforward, and I'm going to start things off with operating pressure. So, the motivation for operating pressure really comes in at low Mach number. So flows with a low Mach number, far less than 1. What we find under these conditions is that the pressure drop in the flow is typically very small compared to the overall static pressure of the flow. That's a statement you'll usually find written down in various CFD manuals and all over the internet, but what does it actually mean? That's what I'm going to dive into and look at a bit today. What that really means is that if the flow velocity is very low and the Mach number is very low, then the characteristic pressure changes that you'll see in the flow field, if you look at contours or line plots, may be of order a few pascals, whereas the background pressure may be atmospheric, maybe a bit smaller, maybe a bit higher, but the overall pressure will be in the region of 101 kilopascals, which is much larger than the pressure changes in the flow. And what you'll see quoted in various CFD manuals and help books is that round-off error can affect the solution. So what does that really mean? The way I'd like you to think about it is to consider the two colour bars that we've got there on the screen. And these colour bars might appear if you plot contours of static pressure from your CFD solution, perhaps for flow over an aerofoil or flow in an internal domain at atmospheric pressure. And what you see in the top colour bar is the range of pressures you may see if you plot the static pressure. And you can see at the low end we've got atmospheric pressure 101,325, and then perhaps with a small pressure change in the domain, the maximum that you may see in your contours would be 101,328. So only a change of a few pascals in the domain relative to that overall background pressure, which is much larger. And what we see is that actually, because the changes in static pressure are very small, then if we consider the digits in the pressure, we see that those changes in static pressure only affect the 6th digit, so the 6th significant figure. And we can really see the importance of this if we then subtract that background pressure from our overall pressure, and this is termed the gauge pressure. That's P sub G. And in the second colour bar there you see actually the range of the pressure changes is only 3 pascals, but we get many more significant figures of resolution there. And again, that may not seem like a problem at first glance, but particularly in a very complicated flow field there may be some very small and very minute pressure changes that we need to resolve accurately, particularly if our cells are very fine or not of a high quality, and we need to resolve those pressure changes if we want to get an accurate overall solution. So there we can really see the motivation for an operating pressure. We're going to take the large background pressure and subtract it from the overall static pressure, and we'll solve in terms of the gauge pressure. That's P sub G. And just as a side note here, this is something that may help you to think a bit more about what the operating pressure and the gauge pressure are. It's very similar to the situation when we have a free surface flow. So if we think of a classic free surface problem where there's no fluid motion, and below the free surface of the liquid, of course, we have a hydrostatic pressure variation where the pressure increases from atmospheric on the surface, that's 101,325, and then increases linearly with depth. And the approach we're taking here, and the approach that the CFD solvers often take, is to subtract the atmospheric pressure from the static pressure variation. So rather than using the figure on the left there with the blue line, we're going to subtract the 101325, and we're actually going to work with the gauge pressure, which is shown on the right there. So we only model the hydrostatic pressure variation and treat the free surface as a fixed static pressure of 0. So that's really what the operating pressure and the gauge pressure are. But how does that manipulation affect the equations that we're going to solve? So if we think of the typical Navier-Stokes equations that we might be solving, that top equation there, if we take the pressure gradient term, which is given by the underbrace, and we subtract that operating pressure, P sub naught, of course, this is a gradient operator. We don't care about the actual value of the quantity, we only care about the differences in the field. So of course, the pressure gradient term remains unchanged by us substituting an operating pressure from it. And that gives us equation 4, which is the form that the CFD solvers use, which is minus the pressure gradient there, which you can see with the underbrace. But of course, a few of you may have noted that this isn't the only change to the equations we're going to have by subtracting an operating pressure or a reference pressure. Also, it's going to lead to changes in the density field, and that's because, of course, pressure, density and temperature are linked by an equation of state. And often this equation of state is given by the ideal gas law, and that's what we're going to look at a bit here. So in the typical form you'll see for the ideal gas law is the density, rho, is given by the static pressure divided by R sub u, that's the universal gas constant, 8.314, divided by the molecular mass of the gas multiplied by the temperature. And the reason we use this formulation of the ideal gas law to compute the density is usually in incompressible flow solvers we use a pressure-based formulation for the equations, and that means we solve the momentum equations for the velocity field, and then we manipulate the continuity equation into a Poisson equation for pressure. We use that to solve for pressure, and then we calculate the density from the equation of state, in this case the ideal gas law. And of course that's not the only way you could do it. You could do it the other way around in a density-based formulation. You could calculate the density from the continuity equation, calculate the velocity field from the momentum equations, and then rearrange the ideal gas law and use that to calculate pressure. But today, we're going to use the most common form for incompressible flows, which is a density-based formulation. Sorry, pressure-based formulation, which calculates the density. And if you're more interested in the algorithms that you use to solve the set of Navier-Stokes equations, be sure to check out my video on the simple algorithm, which is also on this channel and goes through that in detail. So, what changes do we make to the ideal gas law to account for us subtracting an operating pressure from the static pressure? Well, the first thing we do is we rewrite the static pressure as the sum of the operating pressure and the gauge pressure. And then the next key step that we do is we remember that for the low Mach number flow, the changes in pressure are very small compared to the operating pressure. And what that means is that the gauge pressure, which we compute, it captures the pressure changes in the flow field, is very small compared to that operating pressure, P naught. Remember, P naught could be 101325, it could be the atmospheric pressure, and is likely to be much larger than the gauge pressure. And that allows us to get this simplified form of the ideal gas law in equation 6, which says the density is the operating pressure divided by the gas constant multiplied by the temperature. Now, the important thing to note here is that, remember, the operating pressure, P naught, we defined at the start of our simulation and as a constant value. We took that constant value and we subtracted it from the static pressure throughout the entire flow field. And what that means in effect is that with this form of the ideal gas law, the density is only a function of temperature and it doesn't depend on the static pressure. And this is a reasonable assumption if the Mach number is low. And for this reason, some CFD codes will refer to this as the incompressible ideal gas law. So you have to be careful when you select the type of ideal gas law that you're using. And we'll look at what happens in a compressible flow a bit later in this talk. So, what happens if the flow is compressible? Well, if the flow is compressible, then the absolute pressure is important, and that's because the pressure changes are actually large compared with that background pressure because the velocity is high. And what does that mean in our colour bars? Well, if we look at the top colour bar there, we see that the changes in static pressure are now actually quite large. And what that means is that we need to solve the flow field for that complete static pressure, and we don't want to subtract an operating pressure. And for this reason, a lot of CFD codes will recommend that you set your operating pressure to 0. So they still use the same formulation where they subtract an operating pressure, but this time you set it to 0. The reason you set it to 0 is so that the gauge pressure, which you see there in the bottom colour bar, is actually the same as the static pressure. And that's the main reason that the CFD codes advise that you set the operating pressure to 0. And of course, if we think what effect this has on the Navier-Stokes equations, we're now solving the complete set of Navier-Stokes equations. There's no change to that pressure gradient, as the operating pressure isn't used. The pressure gradient is based on the static pressure, and that's because we set the operating pressure to 0. But what about the ideal gas law? So previously, before, we defined the ideal gas law as the incompressible ideal gas law, which you can see there in equation 10, and density is the operating pressure divided by the gas constant multiplied by the temperature. But if you think back, remember for the compressible flow, we set the operating pressure to 0, so P0 is equal to 0. So clearly we can't use that form of equation 10. We have to do something different. And this is what we get if we use the compressible ideal gas law. So this time we calculate the density using the static pressure, the gas constant and the temperature. So really this time the pressure that we use is the sum of the operating pressure, which we set to 0, and the gauge pressure. And the most important point to take away from this is that when we select the compressible ideal gas law from our drop-down menu, wherever in the CFD code, the density now depends on both the pressure and the temperature. And that's of course correct for a compressible flow because the pressure changes are large. So now I'm going to move on to talk about the reference density and the reference temperature. Now, unlike the reference pressure, choices of reference density and reference temperature only arise due to buoyancy forcing in flows, and they arise due to that gravitational acceleration term which we see on the right hand side of the Navier-Stokes equations. So now we're going to dive into the reference density and the reference temperature in a bit more detail so we can understand why they're needed and what you should set them as. So at low Mach number flows, the buoyancy force is large in comparison with the other terms in the Navier-Stokes equation. And what does that mean? Well, if we look at equation 12, the buoyancy term, that rho g, is on the right hand side, and this term is typically larger than the convection term, the pressure gradient and the diffusion terms when the Mach number is low. That's because the velocities are low and the pressure changes are very low and the density changes are low as well. So that buoyancy term tends to dominate the flow. And it means that small changes in the buoyancy force have a significant effect on the overall flow field. And what that means in practice is that often buoyancy-driven flows can be quite unstable and difficult to solve. And so what we'd like to do is to introduce some form of reference density so we can stabilize these equations and make them easier to solve at low Mach number. Now, of course, at high Mach number, the velocities, pressure changes are much larger, and so that buoyancy force term doesn't outweigh the others in the set of equations, and the set of equations tends to be more stable. So what do we do? The trick with a reference density is we take a reference density which is defined by the user. It may be 1.225 for air or 1000 for water, and we subtract this component of the gravitational force from all the cells in the mesh. So the way to think about this is that at every cell in the mesh we have a buoyancy force, and that will be given by, in this case, 1.225 plus some small fluctuation. And it's that fluctuation, it's the density change that drives the buoyancy force. And so the trick we use to stabilize the equations is to substitute that background value or that reference value of the density, so we're only dealing with those density fluctuations about the background value. And what you'll often see in CFD manuals is that the Navier-Stokes equations are then written in the following form, where the buoyancy force term is modified, where we subtract that component of the buoyancy force due to the reference density. And it's just a small modification, but that's what the equations are doing. We're doing that to stabilize them for low Mach number flows. And another small point to note is that for some CFD codes like FLUENT, it's not compulsory to define a reference density, and in some cases a CFD code will compute it for us. And the way it does that is typically it will average the density over all the cells in the mesh and assume that that's the reference density and subtract it from all of the cells. But anecdotal evidence and experience of others in the field of CFD have shown that actually choosing the reference density should be done very carefully, and for this reason the reference density is often left as an option for the user, and we should think quite carefully about the choice of reference density we use. Usually the background density of the free stream flow is fine for most applications. So just a reminder here of what we'll do to solve that set of Navier-Stokes equations. We use the ideal gas law again, or our equation of state, to compute the actual density, and that could be used in the incompressible or compressible form of the ideal gas law, and then the operating density is set by the user at the start of the simulation, and it's a constant value, and we subtract one from the other, and that allows us to compute our buoyancy force. Very straightforward, and that's all that the reference density refers to. But what about the reference temperature? Where does that come in? So a reference temperature is only introduced into the Navier-Stokes equations if we use the Boussinesq approximation for the density changes. And if we don't choose to use the Boussinesq approximation, then a reference temperature isn't required. And even if we specify one, it's not going to be used, so we don't have to worry about it. And what is the Boussinesq approximation? Well, I've done a previous video on the Boussinesq approximation which goes into lots of detail about it, how it's derived, when we should use it, and much more detailed information than I'm going to provide here. So if you're interested, I thoroughly recommend you watch it. But overall, we use the Boussinesq approximation when temperature variations are small. So this might be for buoyancy-driven flows around room temperature, where the temperature variation is perhaps 5 or 10 degrees. It's not significant. And under these conditions, what we do is we use equation 16, where we approximate that buoyancy force term by this Boussinesq term, which has a coefficient of thermal expansion beta, and then the change in density, rho minus rho naught, is instead replaced by the change in temperature. So what we're then doing is we're taking the temperature changes in the flow relative to our operating pressure, which is what the user will specify, and we use that to prescribe the buoyancy forcing on the flow. So if we use the Boussinesq approximation, we have to choose a reference temperature, and as before, that reference temperature usually will take us the background or free stream temperature in our flow. So another small point to make, that when we use the Boussinesq approximation, a reference density is no longer required. We only need a reference temperature, and that's a very subtle point. And if you go back to my video on the Boussinesq approximation, you'll see why. But generally what happens is this is because the reference density cancels out. So if we take equation 17 to start, it's a very short summary. What we've got is we've got that the reference density rho naught on the left hand side, and then you can see on the right hand side the term with the under brace is that buoyancy forcing term that we've replaced with the Boussinesq approximation, and the rho naught is there on the front as well. And what happens is when we divide through by the reference density, we see that the reference density in the buoyancy force term cancels out, and of course the dynamic viscosity is divided by the density is now the kinematic viscosity, and the static pressure is now the kinematic pressure, following standard practice for incompressible flow solutions. And so we can see in equation 18 that actually, because we've used the Boussinesq approximation, we now need a reference temperature, T0, and a coefficient of thermal expansion, but we no longer need a reference density. That's a very subtle point to think about when you're running your simulations. So just a quick summary of what we've been through here today. We need a reference pressure for low Mach number flows, and this is to account for round-off error. We need a reference density to improve the stability of the equations when we have buoyancy forcing, and we need a reference temperature when we use the Boussinesq approximation. So that's a good overall summary of what to take away from this talk, and hopefully you can use it in your simulations to make a better informed decision about the reference values that you're choosing. If you're interested in some further reading, of course you can dive into your user manual for your favorite CFD code, and I've got the links in the description to this video down below for the ANSYS FLUENT reference page, which is section 8.14.3, and the ANSYS CFX user guide as well. This time the section is 1.2.8. And as far as I'm aware, OpenFOAM doesn't require you to specify operating pressure, operating density, or operating temperature, but you should be very careful to check which version of OpenFOAM you're using and which solver, because they all differ. But generally, the ANSYS solvers require you to specify operating pressures, temperatures, and densities. That about wraps up the talk. I hope you found it useful and interesting. And as always, if you have any comments, suggestions, or questions or videos you'd like me to put up in future, please feel free to leave them in the comment section below, and I look forward to seeing you there.